In the last video, we learned that if you just leave water to itself, it auto-ionizes. So let me say I have two molecules of water. There's some probability, and it's an equilibrium, that one of the hydrogens on one of the waters bumps off and just joins the other one. So you could end up with a hydronium ion. It's an ion because it has an extra hydrogen. So I'll put a plus charge there. And obviously, everything here is in an aqueous solution. I could write aqueous everywhere. AQ. Could write AQ. It's kind of obvious. Water is obviously in an aqueous solution. It's obviously dissolved in water. And then plus a hydroxide ion. This is the water molecule that lost its hydrogen atom or its proton, because we know that a hydrogen atom, or at least a hydrogen ion, if you get rid of its electron, all you have left is a proton. And that's also in an aqueous solution. And we learned that people really care. I mean, we learned about the equilibrium constant of this reaction. And we also learned that people really care about the concentration of this right here, of the hydronium. Or sometimes, and let me write this again, because this is actually what happens, and I went over this in the last video. But sometimes the same exact autoionization reaction will be written like this. H2O dissociating in itself, really, into a hydrogen ion in an aqueous solution, plus a hydroxide anion in an aqueous solution, or a negative ion. These are the same thing, and I write this way because this is actually the state that happens, that you don't actually have these protons just independently. They actually do join onto another water molecule and form a hydronium ion. But these are the same exact concept. But we learned in the last video that people really care about the concentration of, you could pick one of these two. They normally write this one right here. So people really care about the concentration of hydrogen, of your hydrogen ions. And we learned in the last video that just pure water at 25 degrees Celsius, which is room temperature. So let me write that. At 25 degrees Celsius, the concentration of your hydrogen protons, because that's really what they are, or hydrogen ions, is 10 to the minus 7 molar. And then we even said, hey, people don't like to, chemists for whatever reason don't like dealing with negative exponents. So they defined the pH is equal to the minus log base 10 of your hydrogen concentration. And of course, that's equal to minus log base 10 of 10 to the minus 7 for pure water at 25 degrees, which is equal to 7. Fair enough. And you could probably imagine if people took the trouble of constructing this pH thing and saying it's a negative log, they must really care about what the hydrogen concentration of water is. And it does matter in a whole bunch of, especially actually biological systems. All the time people worry about the pH of this or that. And obviously I talked in the last video about pH balanced cosmetics. They're essentially, all sorts of bad things might happen to your skin if the pH of the cosmetic is different than your skin. I don't know if that's a fact, but I guess that's the theory behind it. So there's obviously things in the world that change the hydrogen concentration, that change this concentration. So when we learned about Le Chatelier's principle, we said, hey, if we add more hydrogen on this side, the equilibrium will change and this concentration will go up. And so we would have more hydrogen concentration. I guess on the other side, you could add more hydroxide, and then you would have more OH concentration, maybe a little less hydrogen concentration. So if you care about things that are going to do that to this reaction, you probably want to have a name for them. And the name for them is acids and bases. And I'm sure you've heard both of these words before. So acids, let me write them both down. Acids, acid, and base. Now, just to overcomplicate your life a little bit more, there are actually multiple definitions of an acid and multiple definitions of a base, and they kind of become more and more broad in what they imply. The definition that you're probably going to use the most, or it's the definition that I always use in my head whenever someone says an acid, is it increases hydrogen concentration when you place it in water, in water. And a base is something that increases your hydroxide concentration in water. This is the definition that you're probably going to see in 90%, especially in a first-year chemistry class. And this is called the Arrhenius acid or base. Let me hope I get his spelling right. You should never take any of my spelling words at face value. You should look them up because I'm clearly not a master speller. Arrhenius. Arrhenius with an H. These are Arrhenius acid, Arrhenius base. So for example, let me give you an example. If I were to take some hydrochloric acid, that's actually what it's called, but you could say hydrogen chloride in an aqueous solution. It actually dissociates completely. This is not an equilibrium reaction. So let me put it in this nice, well, let me use a bolder color. This nice one-way arrow, which says, hey, this isn't one of these wishy-washy reactions that go in both directions. This is a strong acid. It completely dissociates in water into, let me put the hydrogen in a different color. It completely dissociates in water into a hydrogen ion in aqueous solution plus chloride, plus just a chloride negative ion in an aqueous solution, and they just float in there. So you could imagine if you place hydrogen chloride in water, you're going to increase its overall hydrogen concentration. And the same exact reaction could have been written like this, just to hit the point home. Hydrogen chloride in an aqueous solution. And then you could say plus H, let me do it in a different color, plus H2O. It's a one-way reaction. It's a one-way reaction, and then you end up with, and I think you understand, you have H. Obviously, not all three of them are H3O. That's too dark. H3O plus, it donated its hydrogen proton to this water molecule, and then you have plus the chloride anion in an aqueous solution. And these acids that completely dissociate, in future videos we're going to look at ones that are a little bit more wishy-washy, that don't completely dissociate. But these acids that completely dissociate are called strong acids. And strong isn't just a nice word that they use in chemistry. It literally means, when someone says a strong acid, something that completely dissociates into water. It's a one-way reaction. And all of the strong acids, I mean, you could probably even guess based on their chemical makeup, but hydrochloric acid is one of them. You also have, hydrogen bromide, another strong acid, hydrogen iodide. You have nitric acid. I think I showed you that in a previous. All of these, when you put them into water, they're just this little H is going to pop off, join another water molecule, form hydronium, and then this molecule right here. In these cases, these are, well, in the case of chloride or iodide, these are halogens, but they're going to go and form negative ions, whatever's left over. Nitric acid, then you have sulfuric acid. You've probably heard of that, very strong acid. Sulfuric acid, and then perchloric acid. These are the strong acids. O4. And these are good to know because if you see them on a chemistry exam, you know that these are going to completely dissociate. And remember, we keep using this word acid. What does acid mean? It means that these are strong acids. These completely dissociate. And if you like Arrhenius's definition of what an acid is, they increase your hydrogen concentration, because obviously when you throw this in some water, all of these new hydronium ions are going to be formed, and they're going to overall increase your concentration of them, and that's why they're called an acid. And now, if you went on the strong base side, by Arrhenius's definition, right? By Arrhenius's definition, a base is something that creates hydroxide ions or anions in water. So pretty much anything, if you look at the periodic table, anything here, any of your group 1 elements, and group 1 elements, your alkali earth metals, that's bonded with hydroxide. If you put them in water, the hydroxide pops off. So let me just ask you with lithium or sodium. So for example, these are strong bases. So if I take some if I take some lithium, let me do nice lithium hydroxide in an aqueous solution. This completely disassociates. Completely disassociates. No equilibrium here. This is a strong base. So what's it going to disassociate to? Well, the little hydroxide ion is going to pop off. That's going to be a minus. It's in water still. Plus a lithium ion right there. So this will always dissociate in water. The same thing as if you have sodium. Sodium's going to do the same thing. Sodium hydroxide in aqueous solution, one-way reaction. You produce hydroxide and some sodium cations. And so you imagine when you put these in water, this concentration is going to go up. It's just like what we did in Le Chatelier's principle, where we said, oh, what if you add some of this or some of that to an equilibrium reaction? Well, how do you add it? Well, in this case, you can add a strong acid or a strong base. Now, everything I've done so far, this is the Arrhenius definition, where an acid increases your hydrogen concentration, a base increases your hydroxide concentration. Now, that is what you're going to see 90% of the time, but there's a slightly broader definition out there, and that is and I don't know the correct, I always say just Bronsted, but if you don't have fancy fonts, it's spelled like this: Bronsted-Lowry acid or base, and I'll say, but if you have good fonts, there's usually this little cross in the O. So I mean Bronsted. Well, Bronsted-Lowry acid. And all of these would also be Bronsted-Lowry acid. But the broadening of the definition is an acid is a proton donor, and a base is a proton acceptor. So let's look at this definition and in the context of everything we've just done so far. So if you live by the Bronsted-Lowry definition, what is a proton donor here? Well, this hydrochloric acid, let me look at this reaction right here. This hydrochloric acid is donating a proton to this water molecule, right? The proton, a hydrogen atom is just a proton. That's an important thing to remember, because it has a hydrogen ion. Because if you get rid of its electron, it has no neutron. It's just a proton sitting in space. So this hydrochloric acid is donating a proton to this water molecule to make a hydronium molecule, and it gave it away. So this is a Bronsted-Lowry acid as well, just as it was an Arrhenius acid. Let's see the Bronsted-Lowry version of a base. Okay, a base is someone who proton acceptor. So this guy, he had this nice little relationship with this hydroxide ion. The hydroxide ion got disassociated, so you can kind of, and it becomes a little bit fungible right here. You can kind of say, hey, this guy accepted this positive charge, or he was, and it's a little bit wishy-washy here, because this isn't, it's not like someone gave it a proton. You can kind of think it as he actually gave away electrons, but if you just look at the final product, okay, he's got a positive charge when everything was done. So you say, okay, maybe that's a Bronsted-Lowry base. Now you're saying, okay, well, why did people even make the trouble of defining a Bronsted-Lowry base when all of the Arrhenius acids and bases could also be Bronsted-Lowry? And well, that's because Arrhenius is you're always dealing with water. Everything's in an aqueous solution. But I drew an example here of a Bronsted-Lowry base. It doesn't have to be in an aqueous solution. So if you have acetic acid right here, that's what's in vinegar, plus ammonia, there doesn't have to be an aqueous solution. What happens? This hydrogen gets donated to the ammonia ion to make ammonium. So this becomes positive, becomes negative. It donated this proton, right? And Arrhenius has nothing to say for this. Because everything he deals with is hydronium and water. But the Bronsted-Lowry definition works in this situation. Now, the last kind of, or the broadest definition, although, there are all these definitions, but you're going to be 90% of the time good if you just know the Arrhenius definition and just know that Bronsted-Lowry and what I'm about to say right now also exists, and that's Lewis acid and bases. Lewis acid and bases. The acid, now Lewis cares about electrons. Bronsted-Lowry cared about protons. So Lewis, instead of saying an acid is a proton donor, a Lewis acid says it's an electron acceptor. Electron acceptor. And a base is an electron donor. Now let's look at it in the context of everything we've done so far. So if this is really an acid, it should be a electron acceptor. And the way you can kind of think of it is you had hydrochloric acid before. When this guy gave away this atom or this proton right there, he kind of kept his electron. So he was kind of an electron acceptor. It's a little bit gray area there. I mean, it's not like he took an electron from somebody else. But this would be considered still a Lewis acid. And if you think about a Lewis base is what? It's an electron donor, right? A Lewis base is an electron donor. So if you have it right here, Lewis base is an electron donor. This lithium hydroxide, when it goes into water, there's a couple of ways to think of it. You can say, hey, it's donating this OH, which has this negative charge, so it's an electron donor. I don't like it's kind of squishy that way, so I'm not a big fan of that definition. And in my mind, Arrhenius makes the most sense, and it's kind of the purest thing. Are you creating hydronium or not, or are you creating hydroxide or not? But just to show that the Lewis acid-base definition is the broadest definition. Here's a case of a Lewis acid-base reaction that would not be considered either a Bronsted-Lowry or an Arrhenius base, because this doesn't have to happen in water. And what you have here is boron trifluoride with a fluoride anion. It has a negative charge. It has this little extra electron here. In this situation, this fluoride right here, or this fluorine anion, can donate these 2 electrons. So we could, let's say that this one right here is this one right here. And what it does is it donates these 2 electrons to this boron complex right here. And so if it's the electron donor, what is it? The fluoride is the base. So this is the Lewis base. And then the electron acceptor is a Lewis acid. So this right here is the Lewis acid. Lewis acid. It's good to know that these definitions exist, and especially if you don't get confused in the future. But for a first-year chemistry class, if you know the Arrhenius definition really well, that's the one you'll do very, very well. And frankly, in my mind, that's the easiest one to contemplate. And that's the one that's going to matter in most of the reactions where you deal with the changes in pH to water, because that's what all the acids and bases do, especially in the Arrhenius case. Anyway, see you in the next video, and we'll actually do some math figuring out the changes in pH due to some acid.